Ladies and gentlemen, we will start our second lecture in the second phase of Lean Six Sigma project, the measure phase. The following topics will be covered in details during the lecture: sampling techniques, sample size. There are different tools for analyzing population data than for process data, so you must be clear about what kind of data you're gathering. Most traditional statistical training focuses on sampling from populations where you have a non-changing set of items or events from which it's relatively easy to select a representative sample. In contrast, quality and business process improvement tends to focus more often on processes where change is constant. Process data give more information on trends, for example, than population data, so are preferred in most cases. Process sampling techniques are also the foundation of process monitoring and control. Of course, it is better to check 100% of our production, if possible. However, in most cases, inspection of 100% production is not possible due to many reasons. Even if the 100% inspection is possible, there are problems with this inspection. In a well-known experiment conducted by an independent research team, 100 defective items were added to a perfect lot of items, and then subjected to 100% inspection. The inspectors found only 68 of the defective pieces in their first inspection. It took another 3 passes to find the next 30 defects. The last 2 defects were never found. Conclusion: as a process, inspection is subject to variability also. Sampling is taking data on one or more subsets of a larger group in order to make decisions about the whole group. It is important for samples to be unbiased. And to do that, the sample must be random, systematic, no samples based on judgment, no samples at convenience. For example, for a population with mu mean value and sigma standard deviation, we take 4 random samples with size 3 pieces per sample, each sample with mean value of xi and standard deviation of si. The random sampling is one of the most popular types of random or probability sampling. The entire process of sampling is done in a single step, with each subject selected independently of the other members of the population. Each member of the population has an equal chance of being selected as subject. In the lottery method, each member of the population is assigned a unique number. Each number is placed in a bowl or a hat and mixed thoroughly. The blindfolded researcher then picks numbered tags from the hat. All the individuals, bearing the numbers picked by the researcher, are the subjects for the study. In random number generator selection, let a computer do a random selection from your population. If the population has many members, a computer-aided random selection is preferred. Example of random number generator selection: consider a population of 150 and the required sample size is 10. First, give each member of the population a number from 1 to 150, so we have a 150 numbers. Second, use Excel with the function randbetween of 1, 150 to select 10 numbers as follows. Stratified sampling is a probability sampling technique where the entire population is divided into different subgroups or strata, then randomly selects the final subjects proportionally from the different strata. The most common strata used in stratified random sampling are age, gender, socioeconomic status, religion, nationality, and educational. Example for stratified sampling: randomly select 2 items from Group 1, and 2 items from Group 2, and another 2 items from Group 3. Let's say you have a population divided into the following strata. Category 1, low socioeconomic status, around 39% of the population. Category 2, middle class, around 38% of the population. Category 3, upper income, around 23% of the population. Randomly sample the categories so that the eventual sample size has 39% of participants taken from Category 1, 38% from Category 2, and 23% from Category 3. So, for a population 5 million classified proportionally into the 3 classes, and the target sample size is 30,000, then take the random sample of 11,700 items from Category 1, 11,400 items from Category 2, and 6,900 items from Category 3. Systematic sampling is a random sampling technique which is frequently used for its simplicity and its periodic quality. The first item is randomly picked from the population. Then, each n item will be selected from the list. The procedure is very easy and can be done manually. The results are representative of the population. 2 steps to be followed. First, the starting number. Select an integer that is less than the total number of items in the population. This integer will be the first subject. Second, the interval. Another integer will be picked, which will serve as the constant difference between any 2 consecutive numbers in the progression. The integer is typically selected, so the correct sample size is obtained. A researcher has a population total of 100 individuals and need 12 subjects. He first picks his starting number, 5. Then the researcher picks his interval, 8. The members of his sample will be individuals 5, 13, 21, 29, 37, 45, 53, 61, 69, 77, 85, and 93. Other researchers use modified systematic random sampling technique, wherein they first identify the needed sample size. Then, they divide the total number of the population with the sample size to obtain the sampling fraction. This sampling fraction is then used as the constant difference between subjects. Convenience sampling is a type of non-probability sampling. With non-probability techniques, the random element is absent. When you need to conduct a study quickly or you are on a limited budget. When you cannot get a list of all the members of a population. When include people who are easy to reach. For example, you could survey people from your workplace or a club you belong to, or you could go to a mall and survey local shoppers. Although it says convenient, it runs a high risk that the sample will not be representative of the population. With cluster sampling, the population is divided into separate groups, called clusters. Then, a simple random sample of clusters is selected from the population. Cluster sampling usually provides less precision than either simple random sampling or stratified sampling. On the other hand, if travel costs between clusters are high, cluster sampling may be more cost-effective than the other methods. To sample from a stable process. 1. Develop an initial profile of the data. population size, n, stratification factors. If you elect to conduct a stratified sample, you need to know the size of each subset, or stratum. Precision, how tightly, within what range of error, you want your measurement to describe the result. Estimate of the variation. For continuous data, estimate the standard deviation of the variable being measured. For discrete data, estimate p, the proportion of the population that has the characteristic in question. 2. Develop a sampling strategy. Answer the following questions. Random or systematic? How will you draw the samples? Who will do it? How will you guard against bias? You want the sample to be very representative, but there is a cost in terms of time, effort, and dollars. The goal is to avoid differences between the items represented in the sample and those not in the sample. 3. Determine the minimum sample size, as in next slides. 4. Adjust as needed to determine actual sample size. In order to calculate the minimum sample size, either the population will be very large, and then we will deal with it as infinite population, or population is limited, and we deal with it as finite population. For infinite population, we have two cases. When the population standard deviation sigma is known, then the minimum sample size will be equal to z times sigma, divided by e, and all to power 2. When the population standard deviation sigma is unknown, then the minimum sample size will be equal to p times 1 minus p times z over e to power 2. However, if the population is infinite, we will use calculated sample size, using any of the previous methods, and make a correction, using the population size, as shown in the equation. Examples for sample size calculations. What is the sample size, if margin of error, or level of precision is plus minus 4, for a variable with a standard deviation of 15? The population is infinite, and the sigma is known, so n is equal to z times sigma, divided by e, and all to power 2. After calculation, we found that n is equal to 54. What is the sample size if margin of error of plus minus 0.05 for a population of parts with no defects is 0.45? The population is infinite, and the sigma is unknown, so n is equal to p times 1 minus p times z over e to power 2. After calculation, we found that n is equal to 381. What is the sample size if margin of error, or level of precision is plus minus 4, for a variable with a standard deviation of 15, and population size is equal to 100? The population is finite, and the sigma is known, so n1 is equal to z times sigma, divided by e, and all to power 2. After calculation, we found that n1 is equal to 54. Recalculate n, for the finite simple size, n is equal to 35. Consider the samples, which shown in table, with corresponding number of defectives per sample. Calculate the expected number of defects in each lot. Please pause the lecture and perform the exercise. From the sample size n, and population of parts with no defects p, we calculate the margin of error e, assume z is equal to 1.96, for 95% confidence level. The following formula will be used. To calculate the expected number of faults in the lot, we will use the number of faults in the sample. Expected number of faults in the lot is equal to number of defects in sample, divided by the sample size, times the lot size. To calculate minimum, and maximum number of defects in lot, we will add and subtract the margin of error from the expected calculated number of faults in the lot. Minimum number of defects in the lot is equal to the expected number of faults minus the margin of error times the lot size. Maximum number of defects in the lot is equal to the expected number of faults plus the margin of error times the lot size. Please compare your results with the solution of the exercise. To access sample size calculation template in SigmaXL, click SigmaXL, then Measure, then click Measure Templates and Calculators, then click Sample Size-Discrete to access the sample size of discrete data calculator. The template gives the following default example: notes for use of the sample size discrete calculator. P is estimate of proportion for outcome of interest. Use P is equal to 0.5 if it is unknown. Delta is desired proportion margin of error. Enter as the half of the width. For example, if the desired margin of error is plus minus 3%, enter 0.03. Enter population size N to adjust for finite sample size. NP should be greater than or equal to 5. If necessary, reduce delta to adjust. Click SigmaXL, then Measure, then click Measure Templates and Calculators, then click Sample Size-Continuous to access the sample size of continuous data calculator in SigmaXL. The template gives the following default example: notes for use of the sample size continuous calculator. Delta uses the same units as the standard deviation. Enter as the half of the width. For example, if the desired margin of error is plus minus 0.25, enter 0.25. Enter, optional, population size N to adjust for finite populations. To use Minitab to estimate sample size for the population mean or population proportion. Click on Stat, then choose Power and Sample Size, and then Sample Size for estimation. Choose the parameter you are estimating. If you want to estimate the mean, put in an estimated value for the standard deviation. If you want to estimate the proportion, put in an estimate for that proportion, or 0.5, if you have no estimate. Make sure Estimate Sample Sizes is selected next to the following drop-down box. Next to Margin of Error for confidence intervals, enter the margin of error that will be allowed. Here is the result in Minitab. Please perform the first activity and send your output by email for assessment. Please perform the second activity and send your output by email for assessment. Please download from the resources the instructional video for sample size using Excel templates, SigmaXL, and Minitab. Measure phase SigmaXL.mp4, sample size Minitab.mp4, measure phase templates.mp4. Thank you, and see you in the next lecture of the measure phase.